Hello friends, in this video we're gonna solve this question. This was requested by one of my subscribers. So here, what is Carnot engine? I'm not gonna write the definition, I'm gonna solve the numerical part only. Okay, so how to solve this question? So here you see the efficiency of Carnot cycle is given 1 by 6. Okay, the efficiency is given, this is 1 by 6. Okay, and efficiency of a Carnot cycle is given by 1 minus T2 minus T1. Okay, and here the T1 is the temperature of the source and T2 is the temperature of the sink, right? Okay, now when the temperature of the sink is reduced, now you see from these two relation we can write that 1 minus T2 by T1 is equal to 1 by 6, right? This is one condition, and if you simplify this, that's going to be equal to T2 by T1 is equal to 1 minus 1 by 6, and that is nothing but 5 by 6, right? And now you see again when temperature of the sink that is T2, it is reduced by 65 Kelvin, then the new efficiency becomes 1 by 3. Okay, let me take a new slide so that I can explain properly. So this was the given efficiency, that is 1 by 6. So we write T2 by T1, 1 minus T2 by T1, 1 by 6, which gives T2 by T1 is equal to 5 by 6, right? This is equation number 1. So when the temperature of the sink is reduced, that means it becomes T2 is the temperature of the sink minus 65 Kelvin, right? T2 minus 65 Kelvin, then the new efficiency becomes 1 by 3. So that's going to be equal to 1 minus T2 minus 65 Kelvin divided by T1. That's what we can write. So hope you have understood what I have done here. So from this equation number 1, what we can do here, from this equation number 1 we can write T2 is equal to T1 by 5 by 6. This is equation number 1. So what we need to do, we need to find the temperature. Here you see, find the initial and final temperatures between the two cycles is working. Okay, so first we're gonna find the temperature of sink and source when the temperature of sink was not reduced, and after reduced, what gonna be the temperature? We will calculate all these things. Okay, now here you see, so let's replace this T2 by this value. Okay, then what we're gonna have? We're gonna have 1 minus T1 minus 5 by 6 divided by T1. Sorry, it's supposed to be T1 5 by 6 minus 65. Okay, is equal to so I missed that one. Here is equal to 1 by 3. Okay, so that's gonna be equal to 5 by 6 minus 65 by T1 is equal to 1 minus 1 by 3, and that's gonna be equal to 2 by 3. Okay, so therefore if you simplify this, 65 by T1, that's gonna be equal to 5 by 6 minus 2 by 3. Okay, then that's going to be equal to 5 minus 4 by 6, that's going to be 1 by 6, right? That's going to be 1 by 6. So therefore the temperature T1 is equal to, after cross multiplication we're going to have 65 into 6. Okay, so right, 390 Kelvin T1. So this was the initial temperature of the source. Okay, this is the temperature of the source. Now what going to be the temperature of the sink? Okay, before it was reduced, temperature of the sink T2, let me find. Let us put this value in equation number 1. Okay, just wait, let me clean this. Putting this value of T1 in equation number 1, then what we will get, putting T1 is equal to 390 Kelvin in equation number 1. What was the equation number 1? Let me copy this equation number 1. Okay, so this was the equation number 1. So if we put here, then we're going to get T2 is equal to T1. Instead of T1 we're going to write 390 into 5 by 6. That's what we're going to have. So now here what we're going to have, just give me a second. So if we calculate this, just what we going to have, 390. So first let me divide this one by 3 2 times, then 3 1 is 3, 3 3 is 9, then 0, then 6 5. Okay, that's what we're gonna have. Okay, into 5, and that's gonna be equal to 32, right? So 325 Kelvin. So here you see, as this is the temperature of the sink, this is the temperature of the sink, and this is the temperature of the source. So therefore the Carnot cycle is working between the temperature 325 Kelvin and 390 Kelvin, right? So hope you have understood this. So this is the source and this is the temperature of sink. So therefore the you can say the final, the initial and final temperature, temperature between which the cycle is working are 390 Kelvin, that is the temperature of source, and the temperature of the sink is 325 Kelvin. Or if you if you subtract 273, then you can convert it into centigrade as well, 170 degrees Celsius. And one more question was requested. Let me solve that one also. Let me clean this first. Okay, just wait. So here is the question: 50 gram of water at 0 degrees Celsius. 50 gram of water, mass of water is given here, 50 gram. Okay, and so let it be M1. Okay, it is at temperature T1, that is 0 degrees Celsius. That means if you write in Kelvin, 273 Kelvin, right? And mixed with equal mass of water, again 50 gram, but at different temperature, that is at 80 degrees Celsius. At 80 degrees Celsius, that's going to be equal to, if you add 273 with this, then that's going to be 353, I think. Yes, okay, 353. So yeah, let me check. Yeah, that's correct, 353. Okay, so now you see, when these waters mixed waters at different temperatures are mixed at one at 0 degrees Celsius and another suppose you have 2 cups here containing 50 grams of water. One cup is at 0 degree, another is at 80 degrees Celsius, and the water in both the cups are mixed in another cup. Suppose both are mixed, then temperature of this water in 0 degree will be raised, and temperature at 40 degree after mixing will be dropped, right? And let me consider that change in temperature of the waters in this cup, which is at 80 degree. That means after mixing this water, the equilibrium temperature at which the equilibrium occurs, that is suppose T. So this temperature of 0 degree Celsius raised to T, and it is dropped to T. Okay, let me consider that way. So we know that here you say, so the amount of heat when you mix this to liquid, the amount of heat that will be absorbed to raise the temperature from 0 to T, and amount of heat that will be released to drop its temperature to T, that both will be equal, right? That is the principle that we're going to working with here. And the amount of heat that will be absorbed or released, amount of heat that will be absorbed to raise the temperature from 0 to or you can say 273 to T Kelvin. That means to change the temperature by this much, the heat absorbed will be given by mass of the water, then specific heat, then temperature difference. We know that. Similarly, this heat will be equal to the heat lost to drop its temperature. When this temperature will be dropped, then heat is lost. That's why temperature is dropped. So that is M2, mass of water, specific heat of water. Then so 353, this temperature is dropped to T. Okay, so this is the temperature difference. So hope you have understood this. So in this case, this is temperature is increased to T, and here it is dropped to T, right? Hope you have understood this. So now you see, so here M1 and M2 both are equal 50 grams, so these two will be cancelled. Okay, and S will be cancelled. So if we simplify this, then we're gonna get temperature T is equal to 313. Okay, because you see here we're gonna get after simplifying this 2T 353 plus 273, so T will be equal to 6 here 12, then 6 by 2, that's gonna be 313 Kelvin. That's what we're gonna have, right? So now let me go to the next slide. So change in entropy of 50 gram of water when its temperature raises from 273 Kelvin to T Kelvin. That is T is equal to here 313 Kelvin. Okay, that is given by ds, change in entropy, integration, or you can say here del Q by T. So del Q is given by ms del T, integration from T1, that is 273 in this case, 273 to this is raised to 313, right, and divided by t. Okay, this t is this one. Okay, and this del q is nothing but ms dt, so it is replaced by this term, right? Hope you have understood this. So here are the upper and lower limits, and you see this must be equal to ln integration of 1 by t, that's gonna be log t. So here we're gonna take natural log ln, so the ln t. Okay, ln t. So we have upper limit and lower limit, that is 273 and 313, and let's put the upper limit and lower limit. ms ln t is nothing but here, instead of t, first put the upper limit, then minus lower limit ln, the lower limit to natural log. Okay, so ms, so we know that log m minus log n, that is log m divided by n. So if we apply that, here we're gonna get ln 213 divided by 273. So it can be converted to common logarithm just by multiplying 2.303 log of, now it is it becomes common logarithm, log of 313 by 273. So use you can use calculator to find this value, and if you put the value of m, that is 50 gram, let's put the value of m 50 gram, and specific heat of water, that is equal to 1, and if you put that, then you're gonna get this value 6.829 calorie per Kelvin. That's what you're gonna have. Okay, so now let's find the change in entropy when the temperature of the liquid changes from 353, that drops from 353 to the temperature T, which is 313, right? Let me take a new slide. So here, change in entropy when the temperature of water falls from 353 Kelvin to 313. In that case, ds will be equal to ms. So integrating it falls from here you see 353, from 353 to 313. Okay, so again dt by t. If you integrate this, then again you're gonna get this time 50 into mass is 50 and specific heat is 1 for water, and 2.3026, or you can write 3.3 approximately, into log. So upper limit is 313 now, and lower limit is 353, and if you use the calculator, then you're gonna get this value minus 6.023 calorie per Kelvin. Okay, and so negative sign indicates loss of entropy, and the positive sign, here we have got positive result, so that is gain of entropy. So therefore net change, total gain in entropy, total gain in entropy of the system, that's going to be equal to, so first value we have got 6.829, and here we have got 6.023, and that's going to give you 0.806 calorie per Kelvin. So hope you have understood this. Thank you for watching. See you in the next video. Bye bye.